Yo, fellow kernel hackers, welcome back to Lasergurkenland, reachable under lgl.zillion.com, which is a vanilla anarchy server without much people on it. It's usually empty, and that is not a reason to take the server down. I'm the only person maintaining the server, and I actually do not do much here. I paid the server in advance for multiple years already, so the server won't go anywhere. If you're interested in playing in a vanilla server where you are allowed to hack, where you are allowed to grief, where you are allowed to kill other players and stuff like that, then go join Lasergurkenland. There will be no world resets, and I can somewhat guarantee you that the server will stay online for multiple years, no matter how successful it will be. And this is already going on since 8 months in public manner. My English is the weirdest on the planet, I would say. But yeah, so is the machine done? Just join the server, whatever. I don't feel like talking more advertisement shit. Cool. I think that machine is ready. Is this like... Oh, but this will blow this wall. I'm so stupid. But we can build obsidian here until... Yeah, that's enough. I can still have my flying machine passing through there. If I decide to do so. I mean, I don't actually need to fit a flying machine through here. Because I mean, it's the corner anyways, and I have my TNT tubers there in place already, and one can fly from this direction. Yeah, I could build a full obsidian wall there. I used sand because I thought I have to keep it open so machines can fly through, but whatever, that was like not using my full brain as always, because brain. Yeah, cool. So let's act all smart and nerdy and continue educating ourselves about the Linux kernel. I prepared a video from the channel Hupstream. I've never seen a video from this channel before, as far as I know. It seems to be a talk by sponsored Mozilla. I saw the Mozilla logo somewhere. I don't know though. It's a talk from Stephen Rostedt, and it was uploaded to YouTube on 2017 and has currently 16,000 views. And the title of the video that I'm going to play back now in the background is Kernel Recipes 2017, Understanding the Linux Kernel via Ftrace. Stephen Rostedt. Stephen, did I say Stephen? Oh my gosh, that's so embarrassing. Okay, well, anyways, so if you're interested in kernel development, or in this talk in particular, I can really recommend you to check out the original. Link to that will be in the description. Other than that, I hope to see you in-game on Lasergurkenland, and I'm now going to play back this talk on a second device, so you will have horrible audio quality and no video. And yeah, it's your time to turn off this stream or the re-upload of the stream and just play on Lasergurkenland. Cool.
Is anyone?
Let's go. So that should be fine.
So I'll make my talk quick. I have 120 some slides. If you don't know, my name's Steve Rostedt. I'm the main developer, creator of Ftrace. But before I go and talk about Ftrace and everything, I talk about this talk. First, I'll say I'm a kernel developer, if you didn't know that. Usually I work on the real-time, well, I used to work on the real-time patch until Ftrace became like this, just totally engulfed me. So I originally was one of the preempt RT developers, but now I just mostly focus on this and other fun things. Disclaimer, I'm known to talk fast. I was criticized on Monday for talking too fast in meta recipes, but unfortunately I have so much information. So what I'm kind of doing is I'm giving a 120-minute talk in 40 minutes. This is called compressed presentation. To decompress it, you need to watch this talk 3 times. It's being videotaped. So after this talk, this is one. You have to watch it again. You'll understand a little more. Then you watch it a third time, and there, you totally understand. So for this time, don't really try to understand everything I'm saying. Just kind of...
I wonder how many people actually watch this talk multiple times. I actually sometimes do watch talk multiple times, just because I forget that I watched them already. But yeah.
Over, sit back, relax, and enjoy. I'll try to kind of tell you what to focus on and what not to focus on. My talk may look like this. So,
I have no slime.
Anyway, what is Ftrace? The previous talk talked about hardening the kernel, keeping it secure, keeping people in the scene,
I have to get some
what's
stuff
going on within the kernel, and to be able to exploit it. Ftrace does the exact opposite. It actually tries to show you everything that's going on. I'm sure the security people love Ftrace because we're the ones that enable executable code to be rewritable. We patch kernel. The live kernel patching is actually built on top of Ftrace. When I first made live kernel patching, I said, or not live kernel patching, but first I made the instrumentation that live kernel patching is built on. I said, this is great because there's going to be two groups of people that love this new feature. One is anyone that wants to do live kernel patching, and two, rootkits. So first, how do you get Ftrace? And let me tell you something. Wait, no, I got you.
I love how he calls rootkits people. Rootkits are my favorite type of people. Okay, I'm done, sorry.
With a real camera. Not this cheating with a selfie that shows you what you're taking a picture of. So, how do you get Ftrace? First of all, how many people have heard of Ftrace? Okay, actually I should say, how many people have not heard of Ftrace? Okay, a couple. Now they're like, oh my god, everyone has their hand up, I don't want to put my hand up now. No, that's perfectly fine. It's a kernel thing, and I'm constantly being told by someone over there that I don't market this well enough, and I've given talks all over the world. I don't know how to market it better. Maybe I'm not talking to the right people. So it's in something called TraceFS. It used to be DebugFS, but then we removed the dependency from DebugFS, and we created our own TraceFS. And when you mount DebugFS, which is usually you mount it at syskernel debug, there's a directory that's created called tracing.
How many tries did it take me? And it's still up here. Fucking llama. Just die. Can you not? Thanks. So, now you won't go up there anymore. Cool. There's only one kit left. That's really bad, actually. Is this the kit? Why can I? What heck, mate? Wait, not unbreaking, silk touch. Bruh. It is. Okay. So I really have to dupe it. I don't want to do a dupe session now, but I rebooted my laptop, so I have a mouse. I really have to. Let me get my second mice. No, it's not a second mice, it's a second mouse, and then I have mice. Sorry, native speakers or not stupid non-native speakers for my crazy English. Yes, okay, so we are up and running.
TraceFS on top of that path. So syskernel debug tracing. But if you don't want to mount
what
DebugFS,
do we do?
DebugFS could be prone for those that are interested in security. Debug.fs is probably not the best thing to mount if you're worried about people cracking in your machine. So we try to separate that, and if you have Ftrace enabled, there'll be a sys kernel tracing directory that you could actually mount that just to trace the best to.
Please.
And another thing I wanted to point out is when I first wrote Ftrace,
No.
it was based off of code that was already in the preempt.rt kernel, as well as code that I used throughout my Linux kernel development career. From when I did my first actual real kernel development for my master's in the 90s, and I created.
Are you kidding me? If this is going to continue in that speed?
Time sys, and I even ported my tracing utility to the Zen hypervisor. But that was a predecessor to Ftrace. And one of the most important things for me was I didn't want to build a tool on top of, have a user space tool that had to interact with the tool that I wanted.
Okay, I have to smash it harder, I guess.
From the kernel.
I will.
So I wanted everything to work with just BusyBox. So I was doing a lot of development on for porting boards.
Okay, if this won't work,
when I worked for TimeSys,
I will break my
ported
mouse.
kernel to different architectures, and we had a very limited. We were just lucky to get BusyBox working. I was like, hey,
okay,
BusyBox works
cool.
on this. And once we got that, I wanted to be able to see what's in the kernel.
I have to smash it hard.
So I just wanted to create a file that I could read and write from, and just echo and use normal ASCII writing. So all you need is basically echo cat, and you could use Ftrace. So, oh, by the way, all the slides, I'm assuming is to make it shorter, that it's in syskernel tracing or syskernel debug tracing. So you CD'd into that, and just assume you're there already. So if you look at one of the files, it's trace. So if you have your laptop open in your root and you want to see this, you could actually just see, if you mounted debug.fs, which probably is already mounted, which is kind of funny that most distributions have it mounted, and it's kind of wondering because it's kind of a security issue. Case has to talk about that. But if you go into the directory I told you about and just do cat trace, this is basically what you'll see. Pretty simple.
I thought I know how it works.
Basically available tracers. When I first did the cat available tracers to see what type of tracing utilities I have within my machine, this is all stuff that came up, and I realized, wait a minute, this is my own kernel. I'm testing it. I don't think this is relevant for you guys. So I then switched over to my Debian kernel and did it, and this is what they have, which is kind of interesting that that the lmao tracer. That's actually not part of this talk, but because I don't really even deal with that much. But for any of those that want to reverse engineer binary drivers, the lmao tracer.
Oh, I wasn't even on the.
What it does is it puts in makes all the access to the hardware non-writable or non-readable. And when the device actually goes to access it, it takes a page fault. The page fault goes in, jumps to the tracer. The tracer says, oh yeah, this is mapped here. It will write what the driver was trying to write or trying to read from, and then do the work for the driver. So it's kind of a man-in-the-middle attack between the binary driver and the kernel, or and the device. So it kind of slips in there. But it's interesting that Debian has that on by default. So the no-op tracer is the way to disable everything. That's the default tracer when you boot up the kernel, and if you use any of the tracers, you just echo the name of the tracer into current tracer to change what tracer you want. And when you're done, you just echo no-op and it disables everything. But one of the more interesting ones, if you really want to understand the kernel, what the kernel is doing, is the function tracer. The function tracer lets you see all the functions that are running, basically, almost all the functions that are running inside the kernel. When you just echo function and cat trace, you can actually see all the functions that's happening on your machine live. And this is where we have the live kernel patching, or not live kernel patching, but dynamic modification of the kernel code. This is in that small window that Case mentioned. We enable the entire kernel to be rewritable. And then we go through and we patch all the functions that need to be traced, because there's a no-op place there. We switch that no-op to call into the tracer. And then we switch everything back to read-only again. So during that one time, it changes the kernel to be able to be cracked. But that's why I always keep Ftrace as a root-only utility. More interesting, actually one of more beautiful tracers is built on top of the function tracer. is called the function graph tracer. And what this kind of gives you is a more C-like flow. It shows the graph calls in a C-type looking at it. So if you look at the example I had where it starts off with do syscall 64, and then that calls syscall, or syscall trace enter, which is funny because it's tracing itself. I wonder if I had syscall events enabled. Then does a few other things, and the new sys reads called. Don't worry about that. He said you watch it again, and these slides are going to be available. Tracing on inside the tracing directory, the tracefs directory, is a file called tracing on. This is a way you could stop tracing. You could have any application could open this as long as it has permissions, being root. You can open up this file, and when you want to disable tracing or stop tracing, you just write 0, the ASCII 0, into that file, and tracing will stop. It doesn't actually stop tracing. So the function tracer is still going on. Events or anything you have that's running as for the infrastructure for tracing is still going on. So the overhead is still there. It just stops writes to the ring buffer. So it's this way. You could, if you're trying to debug something, and when you detect, hey, something weird just happened here, echo 0 or write 0 into the tracing on file. It stops tracing, and then you can go back and look at your trace and see what everything happened up to that point, and it won't overflow your buffer. And I have a typo here. It's supposed to be echo 1. So you echo 1 to enable it back again. Yeah, I've done that before. And of course, then there's the one thing is beware of what I just wrote there. Anyone see the bug? Yes. You need a space between the 0 and the greater than sign. Otherwise, you just wrote standard input into tracing on. So bash commands, this is one of the flaws about having like a bash commands doing all this work. To limit the tracers, as one of the props commands doing all this work. So otherwise, you just wrote between the 0 and the greater than sign. Otherwise, you just wrote standard input into tracing on. So bash command, you need a space between the 0 and the greater than sign. Otherwise, you just wrote standard input into tracing on. So bash commands, this is one of the flaws about having like a bash commands doing all this work. To limit the tracers, as one of the problems with function tracing and function graph tracing is it's just overwhelming of information, and a lot of times whatever you do, you're just going to overflow any buffer size you have. You can make like almost a gigabyte buffer, and you can overflow it in seconds, not even, or less than a second. Because when you're tracing every single function inside a kernel, you can imagine that's a lot of data. So you want to limit that. So the way you modify these functions, or modify these files to limit things, is you just echo the name of the function you want to filter. For the set Ftrace filter file, I think I had a typo when I wrote that. You echo, it's not filter, I think that's the French version of filter.
Was this a joke?
Sorry, my kernel is English, so it's not, that won't work. So if you echo schedule into that file, it will only trace the schedule function. Then you can use glob matching. So if I want everything that starts with Zen, I put xen with a star. Make sure you quote it, because bash could play games before it writes to the file and writes everything. And you could do everything that starts with ends with lock, or has the word mutex in it. Now, starting with 4.10, they've actually extended the glob matching within the kernel. So the kernel's doing actually glob in there, where you could do things like put a question mark to represent one character, any character, or put a star in the middle of the word. Before this wouldn't work. The globs was very, very simple because you don't want to put too much complexity inside the kernel. But as we were going on and we slowly grew in complexity, someone else decided to add this functionality because I think they needed it someplace else. They said, hey, I need a glob functionality. Ftrace has one, so let's take that code and extend it for our use. So I'm okay with that because Ftrace became more powerful, because now you could put like raw star lock, and everything that starts with raw ends with lock could be, you could just filter on that. Now, if you want to add more to a file, this is just like bash commands. If you're familiar with working on bash, you need the double greater than sign to concatenate or append to the file. If you just use a greater than sign, you're going to blow away everything that's already in there and write something new. So if you want to clear the file and just clear, like, I just want to clear the trace, you just echo whatever. In fact, actually, the echo is optional. You just put greater than sign set ftrace filter. Okay?
And for even better portability and style, use colon greater than, right?
And it'll erase it.
So it also works in different shells, I
There's a
think.
file called available filter functions. So you cat that out, and you get this huge list of all the functions that you can filter. You can't filter all functions that are in the kernel because there's certain cases. Ftrace will only trace function that GCC will put a little hook in, and there's certain things that GCC does not put a hook in, and there's places that we deliberately say you can't trace this function. Mainly like internals of the function tracer itself doesn't trace. Some timers you can't trace, and some critical conditions like on boot up, there's things where the way the memory layout is a little different, that if you actually try to put a hook in that memory location, things could crash. So you can't trace those files, but and also any inline functions. GCC won't trace inline functions. But so you can't just look at the code to see what you can trace. You actually have to look at the code and then look at this file to see if that's available to be traced. So here's a quick example of using the set ftrace filter. I just echoed schedule in, echo function, and then cat trace, and there's all the function, or I could see the function schedule being called by what process is calling it, what CPU was on, and what function called schedule. Like you'll see like schedule prep disable. So the function tracer traces the function and records the parent that called it, which is useful. There's certain other fields you'll see in there about whether or not interrupts are disabled. The need resched flag was set. Need resched flag just means that something happened where the scheduler needs to be called. So that's why it's set most of the time when you're jumping in there. What's very important in real-time tasks. Usually if a real-time task wakes up and it wants a call, we want to trace, okay, when was this task wanting to schedule in, and when did it actually get scheduled in. So all your tracing, you can see, oh, here the need resched flag was set here, and we got to follow that and say, oh, here's when it's scheduled. Why didn't it schedule right away? Because once that flag's set, you really want to call schedule. And usually you can't if interrupts are disabled or you're doing something else. Set ftrace PID. This is interesting. You just want to trace a single task. You just echo in the PID of that task. Now, inside the kernel, all processes and threads are the same. They're just tasks. So when I say a PID, it's really a task ID. So it's not the process ID that you're worried about. If you're using threads, you need the PID of the thread. And it gets interesting with namespaces. And that's I haven't played too much with namespaces. So if you have a namespace and you're using ftrace, actually, I don't believe we tried to allow ftrace to actually work in containers yet. There's been a lot of people that want ftrace to work in the containers, and I'm like, the whole point of a container is kind of to keep it separate from the rest of the kernel, and ftrace is your entry into the entire kernel. So I've been arguing that it kind of is counterproductive there to have ftrace available inside a container. So there's been a fight going on there. One little trick, if you want to trace an executable from bash, so if you just want to say, okay, I want to trace just this guy, but I don't want to use any utility, I'm on BusyBox or whatever, you could use this little trick with that SH at the very last line there, the one's highlighted. Echo $, it's basically, it forks a process, and then you're saying, here's my PID for my process, whichever it is, whatever it picks, the double dollar sign will be your PID. Write that into set ftrace PID, echo 1 to tracing on. If you notice, I echoed 0 first, although that's kind of doesn't matter. And then execute my program. And then when you do that, like here, I just ran it real quick, and I did it with just exec echo hello. And here, you can see only the echo function was traced. So that's a little trick. Now, system call functions. I call this hack mode because when you want to look at what a system call is, and I'm sure most people here understand that system call is the order where you have when the user space jumps into the kernel. You watch, you go to glibc or wherever, and you look at the code there. When you do a printf, the libraries do a bunch of work, but eventually there's going to be a system call where it asks the kernel to do something. And now this is where, if you want to know what's going on, and this is something that I wish I had when I was learning the kernel, because I want to see what is that next step. What is this black box of the kernel? I could look at the code and I could actually use GDB and whatever follow through, and then it calls this system call, and then it disappears, and then comes back. I'm like, well, what's in there? So I need a way to find where is it in the kernel. If you grep for read, there's a lot of reads, there's a lot of writes. Now, what we usually do is we used to call, all system calls used to be named with sys underscore, the name of the system call. So you could search that search for sys underscore syscall, or your sys underscore read, and do a search for that, and you'll never find it. And what happens is you'll find something like this macro, this weird macro called sysdefine. We have 7 of them, 0 to 6, which means that is how many arguments that system call takes. So if you take it like here, read takes 3 arguments. The file descriptor, the buffer, and the size. So it's syscall 3. So if you're looking in the kernel, you'll see this. And there's also a little problem due to, I guess, to handle sign extensions between different architectures and stuff like that, or if you're using 32-bit, a 32-bit user space with a 64-bit kernel, we had to watch out for sign extensions. So what happens inside this macro to handle that, it creates an alias, or you'll see a sys underscore or sys lowercase underscore read if you ever look at the KL sims, and you'll also notice a capital S little y capital S underscore read. You're like, what the hell? You get these two names for one system call with the same address, and this is kind of confusing, and it confused me for a while until I realized what it's there for. And the reason why I bring this up is because when you write, if you're going to filter on Ftrace picks one of those. Now, unfortunately, it picks the wrong one. Ideally, it would pick lowercase sys underscore read, but no, because the way the linker does it, the capital S is always first. And that's the one that KL sims will return and say, here, because it takes an address and says, give me, Ftrace will ask, at this address, what's the name of the function? And KL sims says, capital S, little y, capital S. So if you write echo little sys underscore read into your file, you'll get this invalid function. I might write code. I plan on just putting in a little wrapper there once to say if you put sys and it doesn't find it, it'll try I might put in something to make that work, hopefully in the future. So what I did, if you grep with a -I.
Short concentration. This one is pushing first, so this is the one we want to activate, right? Replace it here. That didn't work out. Oh! I placed them wrong, right? So it's like this. And now this one, yeah. Did I also place those? Isn't it like this? And you go like, is it stuck somewhere? No, it's not. Oh yeah, it is. Okay. Yeah. Cool.
For sys read and available filter functions, you'll see it's capital S, little y, capital S. So that's if you want to trace a system call, you need to know this. So now we want to learn what's happening in the syscall, the read syscall. So I pull up my code and I see this function, and I'm like, okay, here's the read system call. Let's see what it does. Well, first thing it does, it takes the file descriptor and it's going to give me find a mapping from current. So everyone knows how file descriptors works. It's just an integer. It's an index into some array within the kernel, and so the first thing the kernel does is go into that index and give me something like a structure, a data descriptor, a true data descriptor that could represent this file descriptor. And then it says, oh, this file descriptor actually exists, so let's do some more work. And it does give me the position of the file, and then it calls this VFS read. And I'm like, okay, let's see what this VFS read is, the virtual file system. So I search the code, and I'm like, oh, here's the data. I start walking down, protection, verifying that the area, everything's correct.
I should have known that that the whole thing will explode because
everything's good. And then I'm like, oh, here's another function call that's what I call. It calls another VFS read, underscore VFS read. Really informative. So I jump there, and I'm like, there's a VFS read here. Let's go see what this does. And the kernel loves function pointers. It's an object-oriented designed language. It's C. It's not an object-oriented language, but the kernel's kind of a little bit in an object-oriented model, where you basically have classes that are just structures with a bunch of function pointers, data and function pointers, which is great. It makes it flexible, but when I was learning how to do the kernel, it was god awful. So I see this file fop read. Okay, where do I go now? What do I search for? What do I look for? I'm lost. So I look at what's file. File is this struct file pointer. Okay, let's see what this fop is, because right now it's a double layer. I mean, it's not just read. It's not file pointing to read. It's actually file pointing to some fop pointing to read. So I go and I search. I find struct file. Hey, and there's this thing called struct file operations with a fop pointer. I'm like, what the hell is this? I'm like, okay, let's go and grep for it. 2,885 instances of this crap. Usually, okay, if I know if I'm in the XFS file system or ext3 or whatever, I could actually kind of narrow that down. But still, every time I hit a file pointer, I'm like, oh crap, really? So this is where the setGraph function comes. I'm going to talk about the setGraph function. I use this actually whenever I want to learn a new subsystem of the kernel. I use this today. I mean, not actually today, but I've used it recently within this year. So I'll do this with networking. If there's a driver I plug in, I want to know what's going on in the driver. I'll use this to say, what functions does this call? Let me follow this. So you could modify this file the same way you could modify the set Ftrace filter file with all the globs and everything. You disable it the same way. You write nothing into it. And again, like I said, it has the same issues as the other one. You have to be careful.
Okay, how many machines survived?
So this time I'm going to echo
just one
to setGraph function. And now, if you notice, it will only trace sysread. It traces nothing else. So when it hits sysread, it'll start tracing, and when it gets out of sysread, it stops tracing. So this way I can narrow down what's happening. So I can walk down this and look. There's first the VFS read is, and I noticed down here VFS read, and it called new sync read. I was like, wait a minute. I thought it was the fop read. It didn't even call that function. It did the else statement. So I was going down the wrong path anyway. So I'm like, oh, it's new sync read. Let's see what this does. Well, new sync read goes down and calls call read iter. Call read iter. Oh God. You gotta be kidding me. Here we go again. Luckily, with function graph tracer, I can see exactly what it called. And there it is. Access file read. So now I can jump to there and say, let me just trace that guy. And I want to see what that's doing. But then I get all these things that I don't care about. This condition resched. Let's just say it starts filling up my trace. And I'm like, darn it, I'm getting sick of these condition resets in here. I only have so much buffer that I could trace, and there's this condition reset being called a lot of times. Let's turn it off. So I put it into the no trace file, and now I run it again, and I don't have any. Those functions are not traced, and because of the dynamic modification of code, it actually speeds up the trace. So whenever you filter out stuff, those are all no-ops. So they're not affecting the overhead at all. So if you only trace 2 or 3 functions, in fact, that traced several hundred functions before, ran a bunch of benchmarks, and I couldn't see any issue with there's no change. So this function tracer only takes a few nanoseconds per, well, I shouldn't say a few, maybe a few hundred nanoseconds per trace, which is still pretty small. So it really doesn't have much overhead. But when you trace all functions in the kernel, you have quite a bit of overhead, usually about 10 to 15% overhead in the kernel. So I look at this thing and I'm looking at the file here, and I see some other stuff being called. And I look at XFS transalloc, and let's say I don't want to trace this. I don't care about this function. Yeah, it's allocating something. I want to skip over this. I don't want to trace this. So first thing, of course, you're going to try is to you might write it into the set ftrace no trace because you don't want to trace it anymore. Notice, very important, greater than, because I still have condition reset in there. I don't want to blow that away. So I only want to remove, or I want to keep both. I want to keep what's already in there and add something else to my trace. So I echo the XFS transalloc into that file, and I'm like, okay, let's see what happened. Look, everything that's in blue right there. I don't care about this stuff, because this is what, it didn't trace the XFS transalloc, but it still traced everything that it called. So I want to turn that off too. I'm not interested in that. So, oh, by the way, I just got interrupted. So I'm interrupting this part of my talk to talk a little bit about interrupts.
Haha.
When an interrupt happens, the function graph tracer will tell you, hey, you were interrupted. See that crazy line right there, all those equals and a greater than sign?
I don't know, microphones in the audience, or why it's nobody reacting to his awesome jokes?
It's an interrupt came in, and right there you saw the timer jumped in. But we'll come back to that. Back to our normal program. So, like I said, remember to use greater than, and not just a single greater than if you want to remove something. So right here, I'm going to remove just that line I just entered. So if you see I have both the condition reset and my transalloc, I just want to remove that. So to do that, you slap in a not, the exclamation point saying, okay, not this. You need quotes because Bash really hates or loves to do crazy things if you put a little exclamation point in your line. So quote it, echo it, double greater than into the file, and then it removes it. So this time I use set graph no trace. So there's a set ftrace filter, set ftrace or set function filter, set ftrace no trace. So there's a set graph filter.
Oh, I just realized I lose even more slime if I blow the machines up instead of do I want to do that? I don't know.
Graph no trace. This means don't trace the function nor anything else that it calls. So when I put that in, I got what I wanted. I can now just trace and focus on what I'm interested in, and I could ignore some of the other stuff. Trace options is another file that's the options directory is in the tracefs directory. And this is how you can modify how ftrace works, or the functionality of all the tracing. There's 2 ways to modify it. There's actually a trace_options file, which I seldom use, but that was the first way to modify tracing. And then I'm like, it would be much easier if the options directory listed every option, and you can echo 1 or 0 into it to turn them on or turn them off. So the first option I want to talk about is the func stack trace option. I love this. This is one of the things I used a lot. It's to say, at this function, give me a stack dump. So if you want to know, it's like before, this is the opposite of the call graph. So the ftrace call graph at this function shows you everything it calls and back. Let's do the opposite. I want to see, how did I get there? So at some function, I'm like, wait a minute, who called this? How did this function get called? Big warning in red. This is the lovely thing, because this is one of the most dangerous options you could use. You enable this, and you don't put a filter on and enable function tracing. Every single function that gets called in the kernel does a stack dump. You don't actually lock up the machine. Actually, if you have a very fast machine, I remember Peter Zilster, who had this monster machine, was holy crap, this thing really does kill the performance, doesn't it? It will take any machine and bring it down to the speed of a Commodore 64. What's really fun is, when I've done this so many times, I'm like, oh, really? And then I'm like, okay, E, wait for the E to come up. C, H, O, and then finally I turn it off, but it would take me about 20 minutes to turn off this feature. Sometimes I just say, screw it, just power off the box or unplug it or go reset the board. That's actually sometimes a lot quicker. So, first thing you do is always set a filter before you do that. Then you enable it. You enable the option, then you enable function tracing, do your stuff that you want to see the track dumps on, turn off
yeah.
the recording of the trace, and okay.
Do they reach the end if I start blowing before? Looks like. I can also use sponges, so that's fine.
Okay, I've got everything I want, and then turn off that function stack trace. Always prefer to turn that off. Because what happens, this is usually how I can nail this. I'll enable it once, have everything over to work. And then I'll just, turn off function tracing, okay, put the function tracing in, that option is still enabled. And then, boom, my system's down to a halt. So, this is my way of doing it. And if I say, okay, let's do calls, I want to see where schedule is. What functions are scheduled. So, I start off, I don't know, I'll make sure there's function tracing to the save. Push. Then I set schedule. I pat the file to make sure I didn't make a typo. That's another thing I tried. I'm like, oh, I did not realize that the return I'm just going through quick. And I didn't actually, I did a typo in schedule. I wrote the function file, so nothing actually got entered. And then when I enabled it, the system went to a halt again. There was nothing, there was no filter in the function, and all functions were still being traced, so all functions were doing stack dumps. So I always double check. Then I enable a function with a stack option to echo the function.
Maybe if duping is so annoying, I could revive my slime farm. Yeah, let's see.
And do the dump. And here you see what functions are called. Now, one thing is, by default, you just get the name of the functions and the function stacks, which may not always be enough information. Yes, this function called, but where was it called? So there's more options you could use. You can enable the offset to be printed. So there's a sim-offset file. So if you echo one in that, and then do your, by the way, the trace file is something that whenever you read it, it kind of disables tracing, and it's an iterator that goes through the file. It's not a producer-consumer file, so it doesn't. You don't lose the trace by reading it. So you can read it multiple times. So if you have tracing off, if you read the file multiple times, you'll get the same output multiple times. The trace_pipe, which isn't part of this talk, if you use that, that's a producer-consumer. You read that file, it will erase everything in your buffer. That one is for live stream. Like if you actually enable, if you want to see what's being traced, use trace pipe, because that would be a producer-consumer call. And the big difference is if you cat trace while tracing is going on, while the trace is going on, it stops tracing to do the iteration, then enables tracing again. So reading the trace file can actually affect your recording of the trace. Reading trace pipe does not. So I want even more information. I want the full address pointer. Case? I'm sure you love this because it's telling you exactly where the functions are located in the kernel.
Oh,
so if you have this randomized, if you randomize your kernel, hey, Ftrace is the king of leaks. But it's only done for root. So if you get root privilege, then you can do all this. Okay, maybe I should keep my mouth shut. Moving on. cat trace I just want to talk briefly about the other way of modifying it. Ideally, I use the options directory, but just in case if you want to see how to use the file, which is pretty much obsolete, I should probably just get rid of it. But I have backward compatibility. I don't want to break tools. I think I have some old tools or scripts that still use this because this was the first way of modifying it, and it doesn't really hurt to keep it. If you look at what symbol options are there, you just look at the file. If you want to disable an option, you just put the symbol name and put no. Yes, I'm not being really consistent. I think I should put the exclamation point to be no, but no, I put in no. And then that's the original way. It's kind of stupid, but that's what we have. So, on my laptop, actually it wasn't even this laptop, it was my other laptop that I did this screenshot on. I might have actually switched between two different laptops writing this, so it may not be totally consistent. But I want to see, okay, what module is my Wi-Fi on? So I went and I found the IWLDVM module, and that's okay. That's for the that does Wi-Fi for my laptop. And I noticed it has that Mac 8211 module, which is the device for my laptop. I'm like, okay, I want to just see that. What does this function do, or what does the device do? I'm just interested in this device.
Fuck.
Because I want to kind of learn it. So I echo :mod:. That's a way to tell Ftrace I'm interested in a module and in the module name. So it will actually. By the way,
What is going on here? Wait. I should probably not leave the chunk while it's running, I guess. Fuck. Whatever.
breaks up functions by core, and each module has its own list of functions. So you can tell Ftrace, just enable all functions from this module. And that's with the :mod:, echo the Ftrace filter, and boom. Only the modules for that function was, only the functions in that module will be traced. So I do a cat, right, and then here you can see it's just the function, and yes, KLSims actually produces this, and this is actually, it didn't used to do this, but now it does. So if a function has a module attached, or if the function belongs to a module, you'll see the module name popping up next to it on your traces. Another new feature that's, well, relatively new, it's been several years now, you could hook a trigger to a function. There's several triggers today. The three ones that are mostly used, actually two of these actually are used, is you could turn tracing off when a function is hit, you could turn tracing on when a function is hit, and you could do a stack trace when a function is hit. Actually, turning tracing on, I don't think I've used once or twice. I forgot why. I can't remember why enabling tracing when a function's hit is really as important as disable tracing, because you can just let it run and it will just keep filling up the buffer, and it's mostly important to know when to turn it off so you don't lose the data you want to see. Usually, a lot of times there'll be a debug path, like if I'm debugging something and say a crash is about to happen, or just a minor crash, or something didn't go right, there's usually a function that gets called that only happens on the exception path. I find that function and say, hey, this function happens in the exception path of this bug. So I'll set a trigger on that to disable tracing at that point. This way I don't have to modify the kernel. If I'm debugging something, I don't want to modify the kernel. A lot of times it's a customer's kernel, and I have to tell customers, here, do this trace, do these commands. I give them a shell script. Just run the shell script on your computer, do your thing, and then send me the trace data back. And when it hits this function, it turns off tracing. So then I get everything up to that point, and I'm like, oh, here's the bug. The stack trace feature is something I'm so glad I added, because remember how dangerous that option of func stack trace is? Here's its cousin that's not nearly as dangerous. This is the good boy, you know. He's not the evil twin. Func stack tracer is the evil twin of this trigger function. And what this does is you can set a trigger. You can say, I'm only interested in this one function to get a stack trace on. Just put a trigger on it. So every time that function gets hit, it stack traces. So, that's not what I wanted. Yeah, okay. I remember what I'm doing. So let's go back to the function graphics. And I'm looking at this. The first function that gets called in this module is this EEE 80.211RX nappy function. And I'm like, okay, that's pretty cool. Who calls it? I want to see who calls this function. So I echo the trigger to it using the greater than sign because I don't want to blow away my module filtering. And if I cat it or look at that file, you'll see at the very bottom of the line, you'll see the function name with the stack trace. And don't worry about the unlimited thing. That's a feature that shouldn't be used anyway. And then I do a cat trace, run it, and there. This is actually kind of interesting. It kind of shocked me when I actually looked at the what called it. I'm like, wow, this module actually used interrupt threads. It must have did a request IRQ threaded. Because this was not an RT kernel that I was running. It was my normal kernel. In fact, it might have been I think it might have been my Debian kernel. I don't think I rebooted back to my custom kernel. And I was like, wow, it's actually doing, you can see right in there, if you go backwards all the way up, you'll see the all the way down from the IRQ thread, and that gets called, and it does the function, and then it calls a few other things, and jumps to there. So this way I go back into the code and see how my function was called. I could do more information digging by using these features to follow the flow of kernel to say, oh, this is how this works. So one thing you have to, the triggers are a little special, and here I'm again being inconsistent. I probably should have been, but it's too late. I can't really change it. Once you do something, it's space ABI and you can't change things. So when you do something incorrectly, you're kind of stuck with it. So if you just echo into the file without the double greater thans, like I said, it clears the file. Well, it clears only the filtered functions. It doesn't touch any, the triggers are not touched. I shouldn't have done that. I should have untouched the triggers, but I don't know what I was thinking. Anyway, to remove a trigger, you actually have to specify it in the quote with the not sign again, with the trigger name, and pipe it in there, and that's how you get rid of it. Well, back to interrupts. So a lot of times you get to see interrupts. The only reason I'm actually talking about this is, let's say you don't care about interrupts. The func graph IRQs is an option that you could say, you could actually tell the function graph tracer to say, I don't want to trace interrupts. I don't care about them. If they just waste data in my trace. I just want to see a function, because interrupts could happen anytime. And if you're really just trying to do a flow that doesn't really require interacting with a device or a timer or something like that, you just want to see the flow of this. Having interrupts come in, because some interrupts can be very big, and that just wastes up your precious ring buffer inside the kernel. So I've had a lot of people actually ask me for this feature because they go like, I don't care about the interrupts. I just want to see the data. So yes, there's a func graph IRQ. You got the 0 in there, and so when it's enabled,
why is this one not working? Oh, it is. Okay.
You see all the timer interrupts and then you actually see the and when it exits out. Another fun thing is the max graph depth. This is not an option. This is another file that's not in the options directory. It's an actual feature of Ftrace that was added. It was actually added when we were developing the no principle. And I call it, it's basically strace on steroids. It's a way to say when, it tells the function graph tracer only trace the first function that you get, and then ignore all the functions until it comes back out again. So I can actually use this to see how does user space get into the kernel. Now it gets weird because when you enable it, and when a kernel thread runs, it will just trace the first functions that it calls. So you'll see a bunch of functions in there that's by a kernel thread. And you're like, what's this? There's no user space access to this. That's because it's inside the kernel, and that's still just tracing the first function it calls. But all the user space things, you can say, I just want to see how this user space task goes into the kernel, and how long it stays into the kernel. Because that's another thing about the function graph tracer, it does timestamps all the time. So you can see how long it was actually in the kernel and when it came back. So if you're worried about latencies of your how long your system call lasts, actually in the kernel, you could use this. And the first thing you notice, the idle task, whenever you have a task context switch, you get that strange, idle greater than or equal greater than XOR file. That's a context switch within the function function graph tracer. Function graph tracer is a little different than all the other tracers. I just love being inconsistent. But then you can see when it switched to the XOR, you can see all the ioctals that ran, and you can see how like it took a couple took a couple microseconds each. So let's say I want to just look at echo hello again. So I turn off tracing, I set max graph trace to 1, and I don't care about anything else but this echo hello, or I don't care about other syscalls that are being done. So I enable function graph tracing, I do my little trick with the shell script, boom, and then I cat trace, and there. I can see how it starts off. It's weird how there's a mutex unlocked there, but I think that's coming from like when it gets enabled. It's already kind of executing. Let's have to look at exactly the weirdness of that. But then it does a few do syscall 64, whichever that is. Then you also notice what's really nice that's better than strace. You see page faults. So right now it's page faulting in when it's doing the exec. But that's right, it starts off tracing its bash, and then as it's doing the exec, it does a bunch of page faults the executable in before you, and then end that stuff. So you actually get to see every interaction between user space and kernel. How's that? Yeah, there was a 600 microsecond syscall. Yeah, 688, almost 700 microsecond syscall. Yeah, I mean, I did play with it. I don't know. I just did it. I just was doing an example for the slide. I really didn't care about exec, echo hello. So, but maybe there's something you can look at. Say, why is this? And then you can actually trace that syscall by doing just give me the full trace of that syscall now. So function tracing is actually still limited. It's great. It's super powerful, but has some limits, that you can't do. It does entry and exit. It does the function, the parent, but you don't have exit codes. You don't have parameters. You don't know actually what the function's actually doing, except for all you know is what it's calling. This is where events come in, and events are kind of like print Ks within static points inside the kernel that were added. I just checked my kernel. I just looked at all the trace events, all the trace events within my kernel for the Debian kernel, and I found 1,530 events that were there with my modules. They're broken up by systems. So whenever you create a bunch of events, you create a system for it. There's some for interrupts, scheduling, timer, block, file systems, syscalls, devices, and all these other systems. You can enable and disable by system, or you can enable all of them, all trace events in one shot, or you can just do it by system or by individual events. So if you go into your directory, or in that one directory, the tracefs directory, and you do ls events, you get a full directory of all the systems that are there. If I'm interested in the IRQ system of events, I look in there and I can see it has IRQ entry, exit, soft IRQs, when the soft IRQs are raised, which is basically when the kernel says, kick off a soft IRQ now, and then that's this raise for it, and then you can see when it executed. In each event, you'll see these files, and you can enable it individually like that. So the most common subsystems, if you're just playing around with your kernel, that's going to be probably usually the scheduler events, because you can see when tasks are scheduled in and out, when interrupts happen, what interrupts are being called. You get more information on the interrupts. Timers, what timers are going off, why are they going off? I mean, it gives a lot more information. And you even have exceptions for not just a page fault happening, but what faulted. So it gives you information there. And events work with all tracers, and if you just use the no-op tracer, you only see events. So if I just disable all my tracing and I just enable this get IRQ timer, this is you'll see the events that will likely get the scan. Now there's a set event PID. So just like there's a set Ftrace PID or function PID or Ftrace PID, there's functions, the events are separate itself, and it was added by default in the 4.4 kernel, so the earlier kernel was actually exist. So you can filter on a specific and you can do the same trick again. So if I wanted to see what the system calls are, so this is kind of like the Ftrace version of that. So I made a single process. You echo, you enable syscalls. I want to see exception. I want to see page calls as well. So I enable all the and they add to the filter functions all the other children, which is not efficient. The kernel can do that. So there's an event fork option in the options directory that was added in 4.7, and later in 4.12 the function fork came, and that was it should have came in 4.8. I added the event fork and I put it into the kernel. I'm like, okay, hopefully this works well, and I'll do the function fork afterwards. It was written, it was all set. I just had like 1 or 2 minor patches to write to get function fork working. Well, I got distracted to work on something else and completely forgot about function fork. I just thought I did it. And then 4.12, or actually 4.11, Namium Kim said, hey, Steve, I noticed event fork is there. Don't you want a function fork as well? And it looks like you have all the code there to do it. Here's some seriously 20 lines of code to enable it. And I went, oh crap, I forgot about it. I thought it was enabled. So that's why there's a huge jump between the two. So anyway, here's how it works. Like I said, you start off, you enable the whole thing, and then you do your here. You can notice I'm not using the shell script this time because I'm going to be tracing children. I just say, okay, I'm going to trace bash. So I do echo $$ set event PID, and I do echo tracing on or whatever, but you notice I had the event fork option enabled. So I highlighted the cases. You now see what echo, you see bash calling, and then you can see how echo, and then bash and echo actually running together for a while there. Oops, okay, I'm trying to speed up now. So here's a few things, by the way. This is a little trick. I'm almost done. Almost done, it's sort of. You notice a little trick. If I do cat Ftrace, if you notice that I set it, anyone see why this happens? So I echo the event fork. So first the $$ it said, okay, let me see the set Ftrace PID. Actually, it should have been Ftrace fork there. I just had a cut and paste there either. But anyway, each time I did this, it was a different number. Anyone know why? Yeah, it's tracing cat. By the way, real quick.
What?
Yeah, it's tracing.
I don't get it.
By the way, real quick, introducing trace command. Trace command, everything we did today can be done with trace command. And now here's where I'm going to fly through the slides again, and you can watch this on video. So we start off with cat trace. Here's the trace command show. You can do this not from your, you don't have to actually be at the CD directory. You could be in your home directory when you do this now. So everything here is on your home directory as root. If cat available filter functions, you can do lists. For function trace, you just say start the function. For function graph, start the function graph. Cat available filters, you just list -f, and also those things, it will trace for you. For enable function current trailer, here's start this, here's show. So I'm filtering out this scheduler. Remember this little trick here? Okay, it's a little bit different. You can't run this in trace successfully. You have to do a record. You can't just start it. I might add the fact that you could do tracing later. Then you have sysread here. Here's the trace command version. Condition resched. Here's another thing where you start the translation. I'm going to fly through the one that, this one. Remember the whole thing with the function, the func stack trace? I just want to stop real quick on this one. Trace command will actually make sure you have something, it will echo the schedule for you and make sure it actually filters before it enables it. And when it's done, if you actually did the record, or if you do a no-op or something, it always checks to see if that's set and turns it off. So trace command kind of like protects you from that. So doing the symbols, here how you do options, more options, little graph here, and for the modules, do the same thing, going right through, quick, 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 quick. So I just basically showing it.
Fuck. He's just yeeting through the slides. That's crazy.
You pause. Thank you.
Oh my god. I'm not going to pause and read the slides. That's why I'm listening to a talk, so I can hear him talk.
I don't know.
I'm playing a game, mate.
There's a question over there. Where's the box? Yeah. What's it?
So with the Trust CMD, you also have a front-end Kernel Shark.
Yes, and I was going to show it, but as you see, 122 slides. I didn't quite get around to it. But you talked to me afterwards. I could do a demo. I don't have time today.
Okay. There is no update on the commit. since 2011.
Here's, okay, I'll make a great segue. As people know, I've changed companies. I work for VMware. I was given a full-time employee to work on Kernel Shark. The first thing they're doing is they're transferring it from GTK to Qt. So Kernel Shark's going to be written in Qt. It's working on right now. They got it almost up to full functionality, and so we have someone working full-time on it now. So yes, it will be, you'll see updates soon. Thank you. Anything else?
Why is your code allowing to enable the funcstack trace without any filter?
What's that?
Why can you enable the funcstack trace without filter? Why doesn't it return an error when you enable it?
Wait, why does it? Wait, I am confused. Oh, wait, why? Why would you do it there? I thought about turning it off, but it's been one of those things where it was on my to-do list. It's never actually happened, and it's like one of those things I knew I should be doing this anyway. And it's kind of fun just letting people do it anyway, because it doesn't really lock up the same system. Even my slow boxes, you can eventually get out. It just slows it down tremendously, and it's kind of like a fun thing to do at parties.
What?
If someone leaves their machine up and with a root window open, and I'm around, they're like, "What's wrong with my machine?" That's why I never really fixed that.
Valid reason.
What's the ring buffer size? How many events can you record?
By default, you have 1 meg or 1.4 meg per CPU. Because the ring buffer is per CPU, but there's a ring buffer size file in there. I didn't show it in here, but you can modify the size to however big you want. And one of my tests before
How did that break?
Is to bring it up until the system basically says I have no more memory, and it will shut it back down. So I actually have a test case to make sure it doesn't kill the system if you put in too big of a number. Okay,
How
thank
did
you.
that happen? I can hear, like, what happened here? Like, for real, and when? I don't... Huh? Can anyone, please? Yeah, okay, well, the talk is vorbei. Vorbei! Oh my gosh.